So I'd like to congratulate you on a strong showing for your first attempt of the Module 1 assessment. Everyone made a first attempt, and from the breakout of the item analysis, we find that 12 questions were considered easy because based on student responses, 10 were medium questions and 3 were considered hard. The average score for students was 4.25 points, and the average time students used was 50 out of 60 minutes. That's excellent. What we find in lower level classes is that students tend to be more compulsive, and they answer quickly, and they do not fully utilize all the time that's given. The fact that the average student took 50 out of 60 minutes is a good sign. But you had 25 questions, which meant that you had about 2 minutes for each, had roughly 2 minutes and a few seconds for each of the questions. You know, if you divided a 60-minute hour into 25 questions. So that's the breakout for our first attempt. I've sorted the, now let's see, in terms of min and max, the minimum score was a 3.5 out of 5 possible points. So that's a 70. And that's actually what we would expect for an entire class average. Again, the class average was nearly 4.25 points, and the max score was a little over 4.6. So that's an excellent showing for the very first attempt of the first module. So well done. What I'd like to do is spend some quick moments just to walk through the items based on the item analysis that posed the greatest challenge, particularly the multi-answer where there was a low score. So let's look at the first question that posed an issue, and let's make sure we have everybody here on the screen. Good morning, Deanna.
Good morning.
So the first question that posed the greatest challenge for our students in this first attempt of the Module 1 assessment is, there are 3 platform services or system functions, primary functions of an operating system. Now, we talk about the 3 main features or functions, but there is a different context in some of the other slides. These are handwritten notes where we talk about the platform services, right? And so there are most commonly deployed roles, but then there are also 3 primary platform services. And what we're focusing on here is, what is that server doing in terms of its primary purpose, right? Does it perform a storage role, a calculation role, or does it provide bandwidth? Once again, this is additional information in some slides, and pretty sure we glossed over it pretty quickly, but it says, which platform service would be essential for Google's core business, namely AI-powered internet searches? So Google stores a huge database of all of your activity online. So whenever you're using Google and Gmail and any of their free stuff, essentially it's tracking everything you do, everywhere you go, every exchange of information you do on screen, since you started doing anything with the Google prompt. That is permanently stored forever in their database. That's a lot. So storage is one of those things. And if they're working internet search algorithms based on your particular interests at the moment, they have to do a lot of calculation with that database. So it's storage and calculation. Now, bandwidth wouldn't be the issue unless Google was delivering streaming content. So if they were like an Apple Music, if they were a Netflix, if they were a Hulu. Any question there? The 2 students answered all 3, storage, bandwidth, and calculation. A Google search doesn't initially return a lot of data. So, when you go to a Google search, so if I pull up something here very quickly in Google, and I say puppies, well, I get a couple of splash thumbnail photos. I get mostly text, right? That's not the same as starting a 4K high def streaming TV series or movie. So there's the distinction between bandwidth. You consider this to be a relatively low bandwidth. Same thing with email. If you're pulling up Gmail, that's still largely text. Any questions about how the Google interest for platform, primary platform functions is not the same? Going once, going twice. So the second issue that posed a huge problem, this was a multi-answer, which means it was worth more. And the average score was only 5/100ths of a point. So that was,
Professor,
yes.
you're not sharing your screen.
All right, thank you.
You're welcome.
How are we?
Yeah.
Okay. So here we have John von Neumann developed a model for computer architecture that remains the standard for digital devices and systems. Which component is engaged when an OS provides concurrency? So once again, we had a hand-drawn, it was a page of notes that was handwritten. I drew it up by hand. It was the von Neumann diagram in a rough sketch. We indicated that the CPU and RAM are primarily engaged for concurrency. When it comes to virtualization, all 3 zones of does anyone have any questions about this? Does everybody remember the chicken scratch drawing that
Yeah.
Persistence would involve largely zone 3 or IO, right? Input output, because you're dealing with disk storage. So virtualization, all 3, concurrency, CPU and RAM, and then persistence would be, yeah. All righty then. Multiple choice question here. And these will be the last 2 that we cover here. The software developer must select an operating system as a platform for self-contained media centers used for consumer entertainment. So this is a quality of life issue. It's entertainment, but it's not health and safety. It's not government. It's not regulation. It's not military. So reducing the cost of the finished product was determined to be the most important design criteria. You want to reduce the cost more than anything else. Which OS selection would best suit this purpose? I guess that word is supposed to mean best. And if you use Red Hat Enterprise Linux, as one student selected, essentially you'd be paying for a maintenance contract just to get the screen to work. Apple OS X would be the most expensive option, and Windows Microsoft environment would be the next most expensive option. So in terms of overall expense, if you had a business that was doing something very large scale for media centers, That would be one of the challenges that you'd face. Any questions about this item in particular?
No.
All righty. Last item. Unless there are any others. We need to, yeah, I think that's it. So when we look at the others, everything else is pretty solid. Well, there might be a multiple choice item here or there we could look at, but among the possible deployment roles for a server OS. So here we're talking about Microsoft server roles. This is a multiple choice question. And select those that are considered to be leading roles. This is the Three Musketeers slide. Everybody remember the Three Musketeers?
Yeah.
An organization that chooses to deploy one of these is capable of providing effective, scalable platforms and solutions. Choose the option below that lists leading or most common server roles deployed. Well, Active Directory domain services, meaning domain controller, that is a very important role, but there's only a very few servers that are ever used for an entire organization compared to web and email, right? So that would not be the answer. AD rights management services, this has to do with tracking the use of licensed content like streaming music or movies. And then the SQL database server exchange server and web services. Nobody answered that one. But this is a very common, very important and a leading role. It's one of the ones that's listed there. Any questions about this?
Not for me.
Okay. So file server, web server, network server. That's the Three Musketeers right there. Does anyone care to see any of the other questions before we, everybody got these correct. So those don't really require any others that anyone wants to see. Going once. Oh, let me know. All right, I have posted your reconciliation inside module 1. And essentially you have until the end of the week, 11:59 p.m. So whenever we state a date, we're going to just use a little shorthand here. Whenever we give a date without a time, you'll have until the end of the day. And the end of the day technically is 11:59 p.m. Okay. Does everybody understand those two deadlines are equivalent, right? So is everyone familiar with reconciliation and what's expected?
Yes.
Okay. All right, moving right along. We're going to pick up where we were reviewing process management. And one of the things that we were looking at had to do with the fork. Does everybody remember this? One thing in your study guide that provides a little better clarity is that in Unix, fork is used to create the child from a parent process, right? And then the exec function is used to clear the process memory so that another one can load. So we build the child, and then the execute function basically clears process memory so another one can load, and that's from In the Windows API, it's create process. So in Linux and Unix, how do we create a child process? Fork. In Windows, what do? We use create process. Okay. We'll talk about termination and zombies in just a minute. Any questions about this?
Not right now.
So here's an example of a fork implementation in C for Unix or Linux. And then here we're using create process. It's the create process function. Okay. Process termination. So after a process is created and you've spawned some child processes, in order to end them gracefully, and this is kind of an Achilles heel. A lot of system stabilities come from improper termination. So process executes the last statement, then asks the operating system to delete it using the exit system call. Now, I don't want you to confuse exec with exit. Does everybody understand what I'm saying here? We were just talking about exec. Exec in Unix and Linux is used to clear the process memory so that another child process can load, right? So especially in networking contexts where you have, or web servers that are spawning multiple instances of a web page, right? For multiple clients, you're going to have to spawn a lot of child processes, especially for multi-user, multitasking, multi-user operating systems. So exit would be to terminate the process. It says, however, a child may not continue without a parent. So the parent sends a wait to get the status of a child process and then uses abort to halt the process. This is called cascading termination. It's very important that you glean what's going on here when you have child processes spawning from the use of fork in Unix or Linux, because there's a dependency between the parent and the child process. When you try to initiate an exit to terminate it, the child may not continue without a parent. So the parent has to do some, basically has to do some housekeeping. So the parent sends a wait instead of executing directly to get the status of the child, and then uses abort to halt the child process. So exit is used to halt the parent process. Abort is used to take care of the children. And then once all the child processes are finished aborting or closing out with abort, then the parent exits. And that process that plays out is called cascading termination. If you don't understand these subtleties, it can lead to a lot of trouble. Okay, so we're gonna find out about the zombie issue in just a moment. Any questions before we continue? Okay. That's the cascading termination we were just talking about. So just remember that when wait kicks into gear, when you're trying to exit a process to terminate it, and then wait kicks in, it means there's an ORF, it means there's a child, right? Now, if there is no parent waiting, the process is a zombie. If the parent terminated without invoking wait, the process is an orphan. So the difference between an orphan and a zombie is that if it fails to issue a wait to a child process, that means you have a severed parent-child relationship. So let's say the parent is supposed to gracefully issue a wait command, a wait function to a child process. No, in this case, it fails to issue the wait, right? So you have a parent process, it's poorly written, it's poorly crafted, so it doesn't issue a wait, and the child is out here after the parent terminates. That creates a zombie, okay? Now, if the parent completes termination and the child still has no wait to initiate a proper closeout, then the child is said to be an orphan. So I think it's a zombie until it becomes an orphan, essentially. So while the termination of the process is playing out, if the parent is not a good parent and doesn't issue a wait, then the child process, while that's playing out, is considered a zombie. But then after, you know, the parent completely terminates, the child still has no wait, then the zombie turns into an orphan. I know those are kind of goofy terms, but in any case, this is one thing I wanted to share with you. So browsers as an application would be considered the poster child for what happens without appropriate process management. In earlier versions, a browser with multiple tabs open ran as a single process. So if one of the websites was a problem, the whole browser would crash, right? So that's just a case where not minding your P's and Q's with process termination creates a problem. Any questions? Let's advance a few slides here. I know there's a subtle distinction here, but you just have to, I think it's more of a timing thing here. So there's no parent waiting. There was never a wait invoked. Process is considered a zombie, but then once the parent terminates, and again, it didn't invoke the wait. So you have a zombie or an orphan because wait wasn't called. But I think this is, I'm going to research this a little further. I'd like to understand the difference. I think there's another distinction that's relevant here between zombie and orphan. So I'm going to check on that. So yeah, multi-process architecture in the Chrome browser. The idea of creating a sandbox to restrict certain processes when you have so many parent-child processes spawning with the tabs for a browser. So this is just one example of what we were just talking about. Any questions about that before we get into inter-process communication? So the third student learning objective for our second module, there's quite a bit of real estate and conceptual conceptual foundations that are part of this whole interprocess communication, or IPC realm. In order to understand the basics, it helps to look at some of these diagrams and to kind of reflect on them for a while. But essentially, you have different, the important thing to understand is that there are several methods that are used to share data and to communicate between processes. But the two that we're going to look at involve sharing memory. So you have a memory address range that's shared between processes, and so each of those processes is accessing and writing to, so it's reading and writing to that shared memory. And the other basic flavor of IPC would be passing a message. So this one's sharing data in a memory address range. And in the other model, we're basically passing a discrete message from one process to another. Kind of a one-time instance. So this might be more interactive in nature, and this is sort of a one-way asynchronous. Does everybody know what I mean when I say one-way asynchronous? So you don't necessarily have a parent-child relationship between processes. So you can have processes that are independent of each other, but they still have a way to cooperate and to share data in between, right? So you must be able to identify the type of method based on a diagram like the one on the right. Okay. Notice in this diagram the word message queue. So this would be the diagram that represents message passing, and this would be the diagram that represents shared memory. So process A and process B have this really tight, very limited, but since it's just the two that are sharing between, they don't need a whole lot of memory. Any questions? Let's look at some of the related slides for this. It's just a larger view of the same thing, right? When processes exchange information, right, inter-process communication, they can be independent or they can be considered cooperating. So when they're independent, it means that the processes are more isolated from each other and do not affect or cannot be affected by another process. There's isolation. When we're cooperating, the cooperating processes can affect or be affected. So that's an important distinction. That's a very important distinction to make between the type of relationship between the processes that are communicating. So yeah, you see there's all sorts of benefits for this, but it's an important thing to make a decision about how you want your processes to cooperate together as you're designing them. The more there's cooperation between processes, you're going to have a good bit more in terms of error handling and safeties so that they don't step on each other and that kind of thing. The commitment to controls is going to be significant with cooperating processes. And passing messages would be more consistent with independent processes. if they're not sharing a memory address space, they're not collaborating and cooperating to share a given memory address range. So if they're just receiving a message from another process, everybody understand that of these two flavors of cooperating processes, that kind of ties back to the communication models, right?
Right.
So this would be more independent, and this would be trickier to perform, right? This would be interactive. So you will hear about several different problems when it comes to process management. And I'm going to have some links for you to watch some YouTube videos. And there's one about philosophers eating at a dinner table. Have you heard this one? Was that covered in CSC 242 data structures? The philosopher's problem or producer consumer problem?
I can't recall.
Okay. Well, it's a pretty interesting way to explain the problem. If you have inter-process communication, how they interact with each other makes a huge difference here. So for a paradigm, as far as paradigms for cooperating processes are concerned, the producer consumer paradigm is a pretty straightforward model. It almost reflects like client server. If you think about client server and how that's structured, so you have a producer process that produces the information that is consumed by a consumer process. So on a very micro level, it's kind of like what happens with clients and servers on a platform level, on a very macro level. So when you have an unbound buffer, it places no practical limit on the size of the buffer. And a bounded buffer assumes that there is a fixed buffer size. So how you configure and utilize buffers becomes a challenge for the producer consumer problem. So consistent with shared memory solutions, you have this idea of a bounded buffer. One of the challenges that you have with a bounded buffer is sizing it correctly so that you don't have inefficiencies. One of the challenges, so if you have a bounded buffer scenario and you decide, okay, I'm gonna define what kind of memory we have to work with to share memory between two processes. And one of the challenges that you have is properly sizing the buffer. But if you have an unbounded buffer, the other challenge is if you just have a wide open space, there are cases where, due to the lack of definition, you have processes stepping on each other, right? So in this case, you can run out of space and there are performance constraints. In this case, there's no limit to the size of the buffer, so you can have cases where there are resource limitations and you can get ill-behaved processes stepping on each other. Put another way, if you're saying, okay, I'm going to allow only so much memory address space for this process to talk to that process A to talk to process B. In an unbounded buffer scenario, you don't have that definition, and that's fine for systems that have lots of memory and they never run out of memory. But there are cases that, because of the lack of definition, you have challenges with the process, right? So here you have tighter process, but resources are more limited. Here you have unlimited resource, but there may be definition and control problems with the process. I hope what I'm articulating here is making sense. So this is just a coding example of setting up a bounded buffer for producer and consumer. Am I going to expect you to be able to identify what this is about? Well, yeah, if you see something that refers to buffer size, where there's a buffer definition, I might ask you, is this an example of an unbounded buffer or a bounded buffer? And because the size is being defined, the answer would be, well, this is a bounded buffer because we're defining the size. Is that a sensible explanation for what you're looking at here? Yes, no, maybe? And whether we're dealing with, so if I ask you if this is the producer side or the consumer side, you'd see this word and go, oh, that's the consumer side. Oh, that's the producer side. Any questions?
No.
So shared memory, right? The communication is under control of the user's processes, not the operating system. So the operating system is not as, the operating system doesn't play a central role. The user processes, another word for user processes is running applications, right? So the user has a login and they have all these useful apps, and so there you have it. When the user processes to synchronize their actions, that's one of the major challenges. So once again, you've got tight quarters, they have to play nice with each other. So you have limited resources, and synchronization is a major focus of chapter 5, right? So that's why we have multiple chapters when we talk about processes. Kind of have to take a deep dive into how we synchronize memory sharing when we have resource constraints. For message passing, you have protocols. So everybody remembers networking, CSC 243, or at least part of it, yes?
Yes.
Okay. Does everybody remember the bit about network protocols?
Yes.
Right. So you don't see the word buffer and size in this context. You have these two functions as a part of the message passing protocol, send and receive. And there are cases for either a very consistent, well-defined message size versus something that's very malleable, depending on the nature of the process, right? So here you see if processes P and Q wish to communicate, they need to establish a communication link between them. It kind of sounds like a three-way handshake in TCP, doesn't it?
Yeah.
Right. So they exchange messages using the send and receive function. And essentially, when I use the word protocol, I know in networking, we think about exchanges of information being sent and received between systems, but it's a similar context. It's just happening within the same system, right? You establish a link between the two processes, which is almost like a TCP or a UDP session. You have to determine whether or not a link can be associated with more than two processes. So it might be a one-to-one or a one-to-many, a one-to-one or a one-to-many distinction. So a lot of this has to do with design principles, right? If you're going to be creating stability in an operating system and better security, those are concepts that you have to engage. You know, what's the capacity of a link? How much bandwidth can it, how much bandwidth is reserved for that link based on everything else in the system? And this is interesting. How many links can there be between every pair of communicating processes? So if you have process P and process Q, do you have just one send and receive channel? Or do you have multiple channels? Does everybody remember multiplexing in networking? Where you're encoding multiple communication channels over one signal. It's the same kind of idea. Basically, you have two processes and you might have multiple paths for links. And is it unidirectional or bidirectional, synchronous or asynchronous? Okay. We're going to take a short break right now. Does anybody have any questions before we pause for 2 minutes? Please get up and stretch. So I wanted to call this out to you that basically when you're working with process management and we're engaging topics like, you know, how to create parent process, child process, how we terminate, right? The difference between abort and exit, right? When we talk about process in general, there is a tool suite that was created by Mark Rusinovich, who is considered a subject matter expert for Microsoft operating systems. And there's a link, and we will be using this tool suite. We'll be using sysinternals in the context of Windows, either client or server. So you can work with sysinternals whether you're using the server operating system or the client operating system, Windows 10, Windows 8. Also, our Passy Dussault, the free open source, 3 easy pieces. There's additional information about process management that's helpful. So I would encourage you in your spare time, when you're not reading the primary textbook for our course, it's often helpful to get additional perspective. And so chapters 4 through 6 are focused on process and IPC, right? And then there's some finer points. And if you just click this link, it takes you right there. So that's something that I did want to share with you. I want you to notice that message passing is something that's very common in the Linux environment. And I want to say because, and let's just talk about this for a second. The Linux environment is an open source environment, right? So you have a lot of different standards. You have different communities of interest that are building different applications and operating systems in the Linux arena. And they don't all agree. So message passing is a logical choice for them. If you were to do shared memory as an IPC method, it's not that it's completely vacant. It's not something that is absent from the Unix and Linux world, but you have to resolve and reach agreement on things like whether you're using bounded or unbounded memory. And if you're using bounded, what is the size of the buffer, right? So where there are no boundaries poses a problem since data corruption can occur. So you tend to have where you'll see uses for shared memory where there's Linux in the mix. It plays out in one of two scenarios. You have a Red Hat Enterprise Linux scenario where you have higher tiers of software and operating system support. And that allows different stakeholders in the OS and application development scenarios to coordinate and collaborate and so on. But we've mentioned something about Posix, right? So Posix was a standard that was adopted by computer science and computer engineering interests. And essentially, it was an attempt to create standards for process management, file IO, the whole range of OS interests. So, how do you create concurrent processes? How do you virtualize devices? How do you perform IO functions? What kind of calls? If you have some agreement between operating system types with the Posix standards, then you have interoperability. But really and truly, Windows and Apple, the Mac environment, there's tight control over the hardware and how there's more control over how applications are developed in the Windows and Apple environment. So shared memory is something that's easier to pull off in those iOS areas. I just want you to understand that message passing is really solves a lot of problems in the Linux and Unix world. Posix compliant systems are not so Posix compliant, right? So message passing was first demonstrated and pioneered at Carnegie Mellon University, CMU for short, for the Mach OS. The Mach OS was an example of a microkernel architecture, and it eventually became, so it was a precursor to the next operating system. And this was something that Apple was intensely involved with. So some of you may or may not know that Stephen Jobs kind of peeled away from Apple for a time. And then Apple floundered and almost went out of business. And then Microsoft stepped in. But on the sidelines, Stephen Jobs was cooking up something that really was more aligned with the Linux Unix world. And this idea of a microkernel architecture that's more stable. There was actually hardware associated with that operating system, right? So, well, what happened? Eventually, Apple courted Stephen Jobs back to Apple. And when Stephen Jobs returned to Apple, there were some concepts from the next OS, right, that became part of the Apple OS X operating system. The earliest versions of something we talk about all the time, remote procedure calls, was part of this. So RPC, remote procedure calls. Hackers love RPC, and the early versions of RPC implementations were basic implementations of inter-process communication that were very exposed. And let me repeat that. The early implementations of RPC were very exposed. And some of the exploits that resulted are the stuff of legends. So if you do some research in the cybersecurity arena, this is one thing you find out. Carnegie Mellon has a huge legacy. They're really a powerhouse in a lot of computer science and computer engineering circles. And in particular, they have a lot of, they have like an advanced media lab, and like most heavy hitters in computer science and computer engineering, they have a good bit of artificial intelligence and machine learning interests at this point, cloud-based interests, but they're noted for some very interesting developments associated with the early stages of the internet as well. Okay. Everybody see this?
Yes.
So remote procedure calls would involve inter-process communications, but there is something that gets to be a little confusing. When you look at process management, you have this concept called local procedure calls, and it utilizes many of the similar attributes with, again, network protocols and client server methods. You're defining procedure calls between running processes within the same operating system, and yet you're still defining private versus public connections, which one's providing, which one's receiving, and the terminology varies depending on the context. So it can get a little confusing. You'll see references in Windows to local procedure calls, and then in the Mac Linux world, you'll see references to RPC. So that's something to keep in mind. Just remember that local procedure calls, that's a Windows, we're in the Windows context. We're going to get into more Posix stuff in just a minute here. Any questions about what we've just shared?
No question.
This is more information about message passing, the physical component and the logical component, just as we had layers in the OSI model, right? And in the internet model of communications out in industry, you have the same kind of thing in operating system circles for message passing. You have different layers of interests, the physical and the logical. So, and they're interrelated, right? And they're interconnected. Which one is the lowest and most primal and most vulnerable and most unstable? Is it the logical or the physical?
Physical.
Physical is more privileged, right? So essentially, if the applications all have a direct flight to the physical resources, it usually ends up in a clash of the titans. So those are just generalizations, but in any case, right? We're talking about the flow of information and buffering, that's on the logical level. If we're talking about access to shared memory, physical shared memory, that would be on the physical layer. So here the author is explaining more about direct communication and how links can be formed between processes. So a link can be unidirectional, but is usually bidirectional. So if you don't have a system responding, you have a process that's kind of spitting out information and there's no guarantee. Does everybody remember the difference between guaranteed delivery versus not guaranteed delivery? And which one was which? Is it TCP or UDP that's guaranteed?
TCP.
TCP is guaranteed. That's right. So a session is formed and, as opposed to a connection to just deliver data, right? So with UDP, there is no guaranteed, it's unidirectional. So that's just one comparison that might be helpful. The indirect communication. So we're talking about, see the term mailbox? Yeah. Also referred to as what? Ports. Sounds a lot like networking, doesn't it? So which one would indirect communication, which primary IPC method would be considered indirect? Shared memory or message? Well, I don't know. I just kind of gave it away. The word message is right there. So when you're sending and receiving message, when you're using the message method, that's indirect as opposed to direct, right? Oh, no. Okay, so I take that back. Evidently, you can use direct or indirect with the message method. So let me repeat that. So direct communication, indirect communication can be types of message communication as opposed to shared address space. It's just formed differently. So it says it's usually bidirectional. So if you see direct communication, think, okay, that's messaging as an IPC method, and it's most likely bidirectional. And then indirect would most likely be unidirectional if the logic holds, right? Like maybe unidirectional or bidirectional, but I would say there's more unidirectional process there. Send and receive. So you can, so look at these three different types of indirect communication solutions. You can allow a link to be associated with at most two processes. So that gets back to the previous slide where we asked the question, what are the constraints for communication between two processes? Do they only have a single flow of communication between the two of them? And that's what you'd have in this first type of solution. Allow only one process at a time to execute a receive operation, right? And allow the system to select arbitrarily the receiver. The sender is notified who the receiver was. So when you get into multiple communication paths or more than two processes, that's where this last solution becomes critical. So this is more detail about synchronization for the message passing method. And yeah, it says more about the blocking and non-blocking methods. This is an interesting concept here, that if you have both send and receive, and they're both blocking, you have a rendezvous. So, well, what do you need to know in terms of your next assessment? Well, we already said that if you see some code like this and it has the word message in it, then you know it's not a shared memory method. And if you see the word produced, you know it's the producer side of that message process, right? Sender as opposed to receiver. So yeah, this is more detail about the other side of the coin. So when we're sharing memory, we're dealing with buffering. bounded would mean you're defining the size of the memory address, right? So it's just a different way of looking at the same information. So Posix shared memory, this is a method in the early days of Unix when everybody was interested in creating a common standard between all the different flavors of Unix. And then Microsoft wanted to get involved, so they started making Posix compliant versions of Windows. It got pretty messy for a time because conceptually the Linux Unix world and Windows have very different interests as far as how they construct the kernel, how they choose to provision resources of the operating system, and so on. But this Posix model had limited success. And this is probably one reason why. You see the sign of the devil here, 666. That was a joke. Is everybody still with us?
Yeah.
It was still there.
Okay. So there are Posix components to creating processes that interoperate better with other flavors of other flavors of Unix and Linux. So the other side was producer, and this is consumer. So how would you know which one's producer and consumer when you're looking at the code? Does everybody see here, we're configuring the shared memory object. So we're defining the shared memory object, and then we're posting information to that memory object with write, calls that write. Everybody see that?
Yeah.
Okay. On the other side with consumer, what are we doing? We're opening the shared memory object. We're not creating it. We're opening it and we're reading from it. Is that a sensible way to describe this? So I may show you examples of this code and ask you in different, based on different contexts, right? Which one's the consumer, which one's the producer, and there should be some obvious signs on the screen for each. Any questions about this?
No.
So here's more information about if you see MSG send, MSG receive, and MSG RPC, that's remote procedure call. Those are the early implementations of remote procedure call. And I guess you can associate the M for MSG underscore RPC with mock, right? M with M. They tried to give a lot of thought to this when they came up with the mock operating system, the idea that you'd have all of this robust functionality built into the services, remote procedure calls, wait indefinitely, wait at most so many milliseconds, return immediately, or temporarily cache a message. So now it goes without saying, but the more effectively you manage processes, the greater and more efficient your multitasking and multi-user processes are in an operating system. Let me repeat that. The more elegant and more efficient your process management resources are in an operating system, the greater the capacity to multitask and support many more users, multi-user, okay? So in the early days of the internet, people had a view toward multi-user systems. Let's back up here. So we talked about the local procedure call. So if we're talking about how a process similar to RPC in Linux manifests in a Windows system, it's referred to as LPC instead of RPC. And yet, if you go out there and you start going to Stack Exchange or GitHub, or you start Googling terms for this kind of stuff, there's an awful lot of armchair experts that get the terms or the context wrong. So you'll see references to LPC in Linux systems where it's really more of a Windows thing and vice versa, right? So it won't be the first time we'll talk about handles, but a client opens a handle to the connection port. Client sends a connection request. So that's consistent with the client server operating system. Server creates 2 private connection ports and returns the handle to one of the handles to the client. And they use the port handle to send the messages or callbacks. So in the Windows environment, a trick question could be, once the client server IPC is configured for local procedure calls, what is it that's used to send messages and to listen for replies? And you're going to say, oh, it's the port handle and not the port, okay? It's logical extension of port access. Think of a handle as a way to get at and use the port. So it's a logical extension of a port. Any questions about the term port handle and how that's consistent with Windows? This reminds me so much of TCP/IP. It's crazy, but yeah, you have the client it's requesting a connection, right? And then the server responds. And then you have this 2-way connection, and then they can basically pass a lot of communications data back and forth. We'll stop here for today. But to be honest with you, I don't think we're very far from the end. No, we'll pick up sockets and pipes and some more about Java communication on Thursday. Any questions about what we've covered today so far in process? Going once.